Hello everyone, myself Dr. NCH Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to the today's session on Green's Theorem. Today, I would like to introduce Green's Theorem, the statement of Green's Theorem, and then one problem on Green's Theorem. And here, Green's Theorem transforms a line integral into a surface integral. And here, particularly to apply Green's theorem, the line integral should be in a particular form. Coming to the statement, if R is a closed region in xy plane bounded by a simple closed curve C, and if M and N are two continuous functions of x and y having continuous derivatives in R, then the Green's theorem states that line integral m dx plus n dy is equal to surface integral dou n by dou x minus dou m by dou y dx dy. So this is the statement of Green's theorem. To apply this Green's theorem, the integrand must be in the form m dx plus n dy, where m and n are two functions of x and y having continuous derivatives. So to find LHS must be in the form of m dx plus n dy, and to evaluate RHS, first we need to calculate dou n by dou x and dou m by dou y. So here the given functions m and n can be drawn from the given problem itself. Then we need to calculate m with respect to y, n with respect to x, the partial derivatives of m and n. So here the integrand must be in the form of m dx plus n dy, just now I told you, and the function before dx is m and the function before dy is n. Then differentiate m partially with respect to y and differentiate n partially with respect to x. Then we can evaluate the surface integral also. Let us verify this Green's theorem for the problem line integral 3x square minus 8y square dx plus 4y minus 6xy dy, where C is the region bounded by y equal to root x and y equal to x square. So here, first the given line integral m dx plus n dy is line integral 3x square minus 8y square dx plus 4y minus 6xy dy. So clearly the given integrand is in the form of m dx plus n dy. So this is our m and this is our n, because the function before dx is m. So that implies m is 3x square minus 8y square and n is 4y minus 6xy. Now to verify Green's theorem, we need to check whether the line integral is equal to line integral m dx plus n dy is equal to surface integral dou n by dou x minus dou m by dou y dx dy or not. So we need to calculate dou m by dou y and dou n by dou x. So dou m by dou y means the partial derivative of m with respect to y. So while differentiating partially with respect to y, we treat other independent variables as constant. So we can treat x as constant. So the derivative of this 3x square is 0, and for the next one minus 8 into y square derivative is 2y. So minus 16y, that is dou m by dou y. Now dou n by dou x, with respect to x, we treat y as constant. So here we get 0, and then minus 6y into the derivative of x is 1. So the answer is minus 6y. Now we need to find dou n by dou x minus dou m by dou y, which is minus 6y minus of minus 16y. So which is minus 6y plus 16y, which is 10y. So first we have to identify what is m and what is n, then calculate dou m by dou y and dou n by dou x, and then dou n by dou x minus dou m by dou y. Now to verify Green's theorem, we have to show that line integral m dx plus n dy is equal to surface integral dou n by dou x minus dou m by dou y dx dy. Now, let us consider RHS first. What is RHS? Surface integral dou n by dou x minus dou m by dou y dx dy. So, which is, just now we have evaluated 10y dy dx. So, 10 into double integral y dy dx. To evaluate this double integral, we need the limits of x and y. To find the limits, let us consider the given curve. Given surface is bounded by, the curves. What are the given curves? Y equal to root x and y equal to x square. Y equal to root x and y equal to x square. Y equal to root x means squaring on both sides, y square equal to x and x square equal to y. And it is very clear that these two are parabolas, and there are two types of parabolas. One is symmetric about x-axis and the other is symmetric about y-axis. Here we need to identify which one is symmetric about x-axis and which one is symmetric about y-axis. For that we use a condition. The condition is, if the equation is having even powers of y only, then it is symmetric about x-axis. So, if the equation is having even powers of y only, then the curve is symmetric about x-axis, even powers of y. So, here this is a parabola symmetric about x-axis. Similarly, if the equation is having even powers of x only, then it is symmetric about y-axis, even powers of x only. So, here in this equation x is having even powers. So, it is symmetric about y-axis. So, first we need to draw the region in which we need to evaluate the double integral. So, let us draw the curve. Let us draw the region, x-axis, y-axis, origin. Now, the curve y equal to x square or x square equal to y is symmetric about y-axis. So, let us draw that curve. And y square equal to x is symmetric about x-axis. So, this is the region of integration. We need to evaluate the double integral in this region. So, here these two curves are intersecting at 2 points. One is O and the other is A. So, these are the points of intersections. To identify these points of intersections, first we need to know the equation of these two curves. Now, here you can see this bottom curve, this bottom one is symmetric about y-axis. So, this is the curve y equal to x square, and the upper curve is symmetric about x-axis. So, x square equal to y, symmetric about x-axis, y square equal to x, or y equal to root x. This is the curve y equal to root x. Now, the points of intersections of these two curves are given by, so we have y equal to root x and y equal to x square. That implies root x is equal to x square, squaring on both sides, x equal to x power 4. So, x power 4 minus x is 0. That implies x common, x cube minus 1 is 0. So, either x is 0 or x cube is 1. That implies either x is 0 or x equal to 1. Now, we have y equal to x square. So, if x is 0, then what is the value of y? Again 0. If x is 1, then value of y is 1. Therefore, the points of intersections are the origin and the point A 1, 1. So, this is the point 1, 1. Now, in RHS, we need to evaluate the surface integral, that means the double integral. So, one variable in terms of other variable and the other variable in terms of constants. We need to find the limits. For example, if you want to find the limits of y in terms of x, then draw a vertical line in the region of integration. Then y changes from bottom curve to top curve. What is the bottom curve here? Y equal to x square. Top curve is y equal to root x. So, y varies from y equal to x square to y equal to root x. So, for that reason, first let us fix x first. That means we are going to find x limits as constants. Then y changes from bottom curve to top curve. So, x square to root x, and x changes from here at origin the value of x is 0 and at a it is 1. So, x changes from 0 to 1. Hence, we need to evaluate the double integral 1 from with respect to y, where y limits are x square to x and x limits are 0 to 1. So, let us consider the RHS, which is surface integral dou n by dou x minus dou m by dou y dx dy, which is 10 into, now the limits x from 0 to 1, y from x square to root x, y dy dx. So, first we integrate with respect to y. So, integral x from 0 to 1, the integration of y is y square by 2 dx, where the limits are from x square to root x. Then apply the limits. The upper limit is root x, y square. So, root x whole square, which is x minus. So, by 2 we can write outside, x minus. Now, the lower limit y square. So, the lower limit is x square whole square, x power 4 dx. So, this is 5 into x from 0 to 1, x minus x power 4 dx. So, the last integration is with respect to x, 5 into integral of x is x square by 2 minus x power 4 is x power 5 by 5 from 0 to 1. So, this is 5 into 1 by 2 minus 1 by 5, and the LCM is 10, and this is 5 minus 2. So, 3 by 2. Hence, the RHS is 3 by 2. Now, we need to evaluate LHS also. And what is LHS? LHS is line integral m dx plus n dy. Line integral means only one time integration. That means we can integrate with respect to one variable only. But here we have both x and y. So, either we have to transform y to x or x to y, then we can integrate. But here, line integration, what is line integral? Any integral evaluated along any curve or any line. So, here in our graph, so one parabola with respect to symmetric about y-axis and the other parabola symmetric about x-axis, and here this is the point O, A, 0, 0 to 1, 1. So, since it is line integral, we have to evaluate this as sum of two line integrals. One is from O to A and the other is from A to O. So, this is along OA plus along AO. Let us find the line integral along AO first, along OA, along OA. Now, along OA, so once again I will draw that. So, this is the point origin and this is A, and what is this curve? This curve is symmetric about y-axis. So, y equal to x square curve. Along OA, we are moving along this, through this curve y equal to x square. So here, the value of y is x square. That means we can replace y by x square. That means we are transforming y into x. Whenever we transform y to x, we need to transform dy also. That means by differentiating, we get dy is 2x dx. And x changes from here. What is the value of x at origin? O. At origin, x value is 0 and at a it is 1. So 0 to 1. So therefore, along OA, mdx plus ndy is equal to line integral x from 0 to 1. So what is this? Actually, mdx plus ndy means 3x square minus 8y square, 3x square minus 8y square dx plus 4y minus 6xy plus 4y minus 6xy dy. So here we can replace y by x square. Wherever y is there, we can replace it by x square. So this is 3x square minus 8 into y is x square. Here we have y square. So x power 4 dx plus 4 into y, 4x square minus 6 into x into y. Already we have 1x and now x square. So x cube. dy is 2x dx. So that is equal to integral x from 0 to 1. Let us simplify this. 3x square minus 8x power 4 plus 4 in times of 2, 8 x cube minus 12x power 4 dx. And here everything is in terms of x. The integrand is a function of single variable so that we can evaluate this line integral. So integration of x square is x cube by 3, x power 4 is x power 5 by 5, x cube is x power 4 by 4, x power 4 is x power 5 by 5 from 0 to 1. Here we are using the formula integral x power n dx is x power n plus 1 by n plus 1. As we are applying the limits, no need to consider the integral constant c. Now, by applying the upper limit, so here 1 minus 8 by 5 and this is 2 times plus 2 minus 12 by 5. So this is 1 plus 2, 3 minus 20 by 5. So 3 minus 4, which is minus 1. So the line integral along OA is minus 1. Now, next we need to calculate the line integral along AO also. Along AO. So in this direction. And what is this curve? This is symmetric about x-axis. So this curve is x equal to y square curve. So along AO, x is y square. That implies dx is 2y dy. And y varies from, you see here, what is the value of y? 1. Whereas here the value of y is 0. So y changes from 1 to 0. 1 to 0. So therefore, the line integral along AO, mdx plus ndy, 3x square minus 8y square, 3x square minus 8y square dx plus 4y minus 6xy, 4y minus 6xy dy. So this is y from 1 to 0. Now we are transforming x to y. So that's why we have calculated dx also. So wherever x is there, you can substitute y square. So this is 3y power 4 minus 8y square into dx is 2y dy plus 4y minus 6 into x is y square, already we have y. So y cube dy. Let us simplify this. Y equal to 1 to 0. 3y power, this is 3 into 2, 6, y power 5 minus 16y cube plus 4y minus 6y cube dy. Now once again using that formula integral, y power n is y power n plus 1 by n plus 1. We can integrate this 6 into y power 6 by 6 minus 16 into y power 4 by 4 plus 4y square by 2 minus 6y power 4 by 4 from 1 to 0. Now upper limit we get 0. For lower limit minus of, these 2 gets cancelled, 1, 4 times, so minus 4, 2 times, so plus 2, and here 3 by 2, minus 3 by 2. So this is the 1 plus 2, 3, 3 minus 4, minus 1, so plus 1, plus 3 by 2, which is 5 by 2. So therefore, we have evaluated the line integral along AO and along OA. Now, LHS is the line integral along the curve C mdx plus ndy, which is the sum of along OA plus along AO. Along OA, we got minus 1 and plus 5 by 2, which is 3 by 2. And we have evaluated RHS first, that is equal to 3 by 2. Now, LHS is also 3 by 2. That implies LHS is equal to RHS 3 by 2. Hence, Green's theorem is verified. So, to verify the theorem, we need to evaluate both LHS and RHS. And finally, we prove that both are equal. In today's session, I have introduced the statement of Green's theorem, which transforms a line integral into a surface integral. To apply Green's theorem, the line integral must be in the form of mdx plus ndy. Then we can apply Green's theorem and we can convert this into surface integral. We can convert this into surface integral and hence we can evaluate the line integral value. To verify Green's theorem, we need to find both line integral and surface integral, and finally we prove that both are equal. So in the next session, we will continue the same concept. We solve some more problems on Green's theorem as an application of Green's theorem. To evaluate the line integral, instead of evaluating line integral, we convert it into a surface integral using Green's theorem. So that we will discuss in the next session. Thank you.